What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Section 7, Inverses and Radical Functions. Let's do it. So before we can answer why we cannot find inverse functions for all polynomial functions, let's first understand what is finding an inverse function. And let's say we have a nice simple polynomial of y equals x squared plus 3x. The inverse is to replace the x's with y's and vice versa. So it'd be x equals y squared plus 3y. And then if we'd want to simplify or isolate the y to get that actual inverse function, we need to isolate y. Well, the reason why you can't in some cases algebraically, it's just a task that's too big or may not even be exactly possible to carry out that isolation. So that would be the reason. That's it. When finding the inverse of a radical function, what restriction will we need to make? So the restriction you're going to need to make is on the domain, and I'm going to show you why. So for a typical radical function, it's going to start at the origin. It's going to look something like this. This is without any transformations. The inverse of a radical is going to be a quadratic. Like if it's just a square root, right? That's the inverse. But the problem is that a quadratic is actually going to be a parabola, right? And that doesn't look correct because that it should be a reflection across the line y equals x. But I got this whole extra component that isn't here. So that's why we have to put a restriction on the domain, and we say, like in this example, we'd artificially restrict the domain of the inverse to be everything from 0 to infinity, and that way you're sort of cutting it off, and so it actually looks like the correct inverse. So that's what you'd have to do, apply a restriction to the domain, boom, done. So for this one, we're going to start by rewriting this as y equals x minus 4 squared, and then my next step is switch the x's and the y's. Next, we're going to take the square root of both sides. So square root of x is square root of x, and the square root of this side will just kill that exponent, and we get y minus 4. Last but not least, I'm going to add 4 to the other side, and we get y equals the square root of x plus 4. Now, one thing you may want to note is that normally we'd have a plus or minus situation, right, when we square root, but because of this artificial domain, this means that we're only taking the positive side of this parabola. So this actually makes sense. We don't even have to worry about the negative side. The positive side is sufficient. And then last but not least, as we write this in that correct notation, we're going to replace the y now with f of negative 1, or the inverse of f of x is equal to that radical function, square root of x plus 4, boom, done. So for this one, again, we've got this artificial domain restriction. We're starting from negative 1 out to infinity. And again, the vertex is going to be at negative 1. So we're just taking this side of the parabola. And then obviously, if we inverse it, that's going to be perfect because it's going to be a nice radical function and just the positive side. So again, when we take the square root, we'll have a plus or minus, but we're just going to go with that positive option. First, I'm replacing f of x with y. Then the next step is we swap the x's with the y's and vice versa. So x equals y plus 1 squared minus 3. Then we're going to add 3 to both sides. X plus 3 equals y plus 1 squared. Then we're going to take the square root of both sides. And then we got y plus 1 equals. Now again, this should be a plus or minus situation, but as we specified, because we've already restricted the domain to the right side of the vertex here, going from negative 1 to infinity, I'm only having to take this positive root. I don't have to worry about the negative side. So now I have y plus 1 equals radical x plus 3. And then the last step, we're going to subtract 1 from both sides. Y equals rad x plus 3 minus 1. Notice how I switched it so the y is on the left side. It's arbitrary. But then the last step is we're going to write it in our correct notation. F inverse of x, or f to the negative 1 of x, equals radical x plus 3 under the rad minus 1. There's the final answer. Done. For this one, notice that we've got a domain restriction from 0 to infinity. And what this parabola would look like otherwise, right, without the domain restriction, since it's a negative x squared and a y-intercept of 0, 12, it would look like this at 12, kind of coming down like so. But what it's done here is it's saying from 0 to infinity, which means it's knocking off this left side. Now that's just to give you some context. Now let's do the algebra. So we're going to first replace f of x with y. Then I'm going to swap the x's and the y's. Now I'm going to isolate the y. So first I'm going to subtract 12 from both sides equals negative y squared. Divide by negative 1. So, and I'm going to flip this around to y squared equals 12 minus x. Then we're going to take the square root of both sides. And I got y equals radical 12 minus x. Now, normally it'd be plus or minus, but because we've restricted the domain here, we don't have to, we're basically not including the negative side. So this is our final answer. So we can say f inverse of x, or f to the negative 1 of x, equals rad 12 minus x. Boom, done. So for this one, once again, we're starting with a parabola, and we've got a domain restriction from 0 to infinity. So just to get a visual representation, this is going to look something like this. Normally, it would be a parabola going up both ways, starting at the y-intercept of 4. But because it's from 0 to infinity, we're removing that portion. So we're just trying to find the inverse of this. And you can tell, like, visually, because you're going to reflect it across the line y equals x, the inverse is going to look something like this, like some sort of a radical function starting out here. Now let's actually do the algebra, and we'll see that the algebra will confirm our hypothesis. So first we got y equals 2x squared plus 4. Then we're going to swap the y's and the x's. So we got x equals 2y squared plus 4, and then we're going to isolate y. So we subtract 4 like so, and then we divide both sides by 2, boom. And then we got y squared equals x minus 4 over 2. Last step, take the radical of both sides. And again, that's going to be a plus or minus situation, but because of this domain restriction, we don't have to worry about the negative side. So we're going to end with y equals just the positive radical of x minus 4 over 2. And then in our nice function notation, f of negative 1 of x, f inverse of x, is equal to radical x minus 4 over 2. Boom, done. For this one, we're meant to find the inverse function. So again, we start with the step of replacing f of x with y. Then we're going to swap the x's and the y's like so. And now we're going to isolate y. So first I'm going to subtract 1 from both sides, 3y cubed. Then we're going to divide both sides by 3, boom. Then I got y cubed equals x minus 1 over 3. Last step, we're going to get rid of that cube by taking the cube root of both sides. And notice with an odd root, like a cube root or a fifth root, we don't have to worry about that plus or minus, okay? It's just, it is what it is. So then we have y equals the cubic root of x minus 1 over 3. Last but not least, let's get that right function notation. So I'm going to swap out y with f of negative 1, or f inverse of x, equals that cubic root of x minus 1 over 3. Boom, done. For this one, we're going to start by replacing f of x with y, and then we're going to swap the x's and the y's like so. And now we isolate y. So first I'm going to subtract 4 from both sides, and then I'm going to divide by that negative 2. Again, we're just isolating y here. So then we have y cubed equals x minus 4 over negative 2. Then to get rid of that cube, we're going to take the cubic root of both sides. So now we have y equals the cubic root of x minus 4 over negative 2. And in the answers, what they've done is they've taken that negative in the denominator and they bring it up top. So they basically multiply the entire numerator by negative 1, which is a little bit arbitrary, but we can go ahead and do that just to follow suit. So then that would flop these guys into 4 minus x over positive 2. And then we're going to put it in that nice function notation. F inverse of x is equal to the cubic root of 4 minus x over 2. Boom, done. So for this one, we're meant to find the inverse. So we're going to start with y equals replacing f of x with y. And then once we get to this point, we're going to just swap the x's and the y's. So now we have x equals 3 minus 4y, right? Swapping those x's and the y's. And now we're going to isolate y. First, we're going to square both sides. X squared equals 3 minus 4y. We're going to subtract 3. And then the last step is we're going to divide by negative 4. So y equals x squared minus 3 over negative 4. If we want to transfer that negative up to the top, it's just going to flip these guys, and we're going to get y equals 3 minus x squared over 4. Now you might say we're done, but there's one other thing that we have to take into consideration. We had a radical function, and we're only taking the positive side, not the negative side when we graph it, right? So it's kind of looking like this. So if I have a quadratic as my inverse, that's going to be a parabola, right? That's going to be a parabola kind of going down with two sides, but that's incorrect. We don't want a parabola basically like two sides. We want to chop one of those sides off. And the way we want to do that is we want to take the range that we have in here and apply that as the domain of the inverse. So what is the range of f of x? Well, since it's a radical, you can't take any, the lowest this is going to go is 0 when x is 3/4. And then you can't go lower than that because we're not taking the square root of a negative. So the range here is from 0 up to infinity, right? You could have all these values of x being plugged in like -10, -100, -1,000,000. You're going to get bigger and bigger. So that's the range. That's going to be my domain that I'm going to impose on this function. So it's everything including 0 out to infinity. And then last but not least, now we'll replace it with that nice function notation. F inverse of x equals 3 minus x squared over 4 with the domain of 0 inclusive to infinity. Boom, done. For this one, we're going to start by replacing f of x with y, and then the x is going to stay as is. Second step, we're going to swap the x's and the y's. So x equals square root of 6y minus 8 plus 5, and then we're going to isolate y. So first we have x minus 5 as we subtract 5 from both sides. Then we're going to square this guy on both sides, right? Like boom, boom. And then we have x minus 5 squared equals 6y minus 8. Then we're going to add 8 to both sides. X minus 5 squared plus 8 equals 6y. Last but not least, we're going to divide both sides by 6. Make sure we have enough room here. Y equals x minus 5 squared plus 8 all over 6. Now you'll notice that in this original function, we have this radical, and we want to think about what is the range of this radical. Well, the lowest it's going to go is when this zeroes out, and that's going to start at 5. So the range here is from 5 up to infinity. So we need to apply that as a domain restriction for this inverse function, okay? So we can say f inverse of x equals x minus 5 squared plus 8 over 6 with a domain restriction, which was, again, what was the range? It was from 5 to infinity, and that's how you do it. Done. For this one, we're going to start by replacing f of x with y. Then we're going to swap the x's and the y's. And now we're going to isolate y. So first I'm going to subtract 3 from both sides, and I get the negative cube root of y over here. Divide by -1. That just flips this to 3 minus x equals the cube root of y. And then last but not least, we're going to cube both sides, and we get y equals 3 minus x cubed. And to put this in that nice function notation, it's going to be f inverse of x equals 3 minus x cubed. And there's no domain restriction here with this nice cubic function, so this is the inverse. Boom, done. For this one, we're going to start by replacing f of x with y. Then we're going to swap the y's and the x's. And then we're going to isolate y. Now, this one I'm going to start by multiplying both sides by y minus 4. So we get x times y minus 4 equals 3. Then I'm going to distribute the x, and I got xy minus 4x equals 3. Then I'm going to add 4x to the other side. So x times y equals 4x plus 3, right? I'm adding the 4x over there. Last but not least, we're going to divide both sides by x, like so. And now I get y equals 4x plus 3 over x. And now we're going to put this into that nice function notation, replacing y with f inverse or f negative 1 of x equals 4x plus 3 over x. Here's your answer. Boom, done. For this one, we're going to start by replacing f of x with y. Then I'm going to swap the x's with the y's like so. And now we're going to isolate. First by multiplying both sides by y plus 7. So I got x times y plus 7 equals y minus 2. Now we're going to distribute xy plus 7x equals y minus 2. Then I'm going to subtract both sides by y and subtract both sides by 7x simultaneously. So I got xy minus y on the left side equals negative 7x minus 2 on the right-hand side. And the idea is we're trying to get the y's together because now I can factor the y out. And I've got x minus 1, factoring the y out equals negative 7x minus 2. Now to isolate y, I divide both sides by x minus 1. So I got negative 7x minus 2 over x minus 1. Now, one other tiny little step. If you want to take this negative and factor it out of the numerator, drop it to the denominator, you can simplify it as 7x plus 2 over, and then as you distribute the negative, that's negative x, that's positive 1. So just one other alternative way to write it, and then putting it back into that nice function notation, f inverse of x equals 7x plus 2 over 1 minus x for the win. Boom, done. So for this one, I'm going to start by replacing f of x with y. Then I'm going to swap the x's and the y's. So that's going to be x equals 5y plus 1 over 2 minus 5y. And then we're going to multiply out that denominator to the other side. So then I'm going to get x times 2 minus 5y equals 5y plus 1. Next, we're going to distribute the x's, and I get 2x minus 5xy equals 5y plus 1. So what we're trying to do here is we're trying to get the y's together and isolated. So I'm going to add 5xy by simultaneously subtracting 1. So now I got 2x minus 1 equals 5y plus 5xy. Now this is great because I can factor out a y from the right-hand side. So then I got 5 plus 5x equals 2x minus 1. Last but not least, I'm going to divide both sides by 5 plus 5x. I'm going to do it over here. I'm going to also put y on the left side. That's just arbitrary, but then I have 2x minus 1 on top divided by 5 plus 5x, or I can flip that and make it 5x plus 5. Last but not least, let's do that nice function notation. F inverse of x equals 2x minus 1 over 5x plus 5. Boom, done. For this one, we've got the domain restriction here from -2 to infinity. And just so you know, that's actually where the vertex of this is going to occur. It's going to occur at -2. So what this is really doing is if we have a parabola, let's say this is going up like this, with a vertex it's at -2 something. Let's just pretend it's here. But the main idea is when we restrict it, what we're doing is we're going to the right, meaning we've only got this kind of like side with the positive slope, okay? And that's what we're doing the inverse of. And the inverse now is going to look something like this. I'm just saying approximately like a radical, maybe starting here and just kind of flipping across. So that's just something to keep in mind. It's obviously just going to be the positive side of the radical, meaning this is what allows us not to have to worry about the negative side. But let's go ahead and follow the steps and see what we get. So first, I'm going to replace f of x with y. Then I'm going to swap the x's and the y's, and I'm going to make it x equals y squared plus 4x plus 1. Then I'm going to swap the x's and the y's, and I'm going to make it x equals y squared plus 4y plus 1. Next, what I'm going to do is, in order to isolate y, I'm going to complete the square, okay? So I want to complete the square by basically taking half of the middle term, which is 2, half of 4 is 2, and then square it. So I'm going to add 2 squared, aka 4, to both sides. So you see now with this here, this is a perfect square trinomial, which means I can factor it to be y plus 2 squared. It's literally, that's what it is. And if you want to test that out, if you don't believe that that's the right thing, just do y plus 2 times y plus 2, FOIL it out. You'll see you'll come right back to this. So then we have the plus 1 out here. Now it's going to be easy to isolate. Now I can subtract 1. I got x plus 3 equals y plus 2 squared. Then I'm going to take the square root of both sides. Again, that's a plus or minus, but as we mentioned at the beginning, we don't need the negative side. So I can just say now, and let's flip it around, y plus 2 equals the positive square root of x plus 3. Last but not least, we're going to subtract 2 from both sides. So we got y equals radical x plus 3 minus 2. And then we're going to put in this nice function notation, f inverse of x, or f negative 1 of x, equals radical x plus 3 minus 2. Boom. Done. So here we want to start by finding the inverse, which entails first writing it as y equals x plus 2, then swap the x's and the y's. So we got x equals y squared plus 2. And then we're going to isolate the y. So I got x minus 2 equals y squared, and then we square root both sides. Now, normally that would be a plus or minus, but because of that initial domain restriction, we're just going to take the positive side of this. So that gives us a final answer of y equals square root of x minus 2. But in function notation, it's f inverse of x equals radical x minus 2. Now we're going to graph both of these functions. I'm going to actually do so in Desmo so you can see the relationship between the original function and the inverse. So you'll notice here we have the original function and the inverse, but they should look the same, but just one reflected across this invisible line of y equals x. So it almost looks like that, except for this part here. But that's why we have to have that nice domain restriction. X is greater than or equal to 0. And then when you look at the two graphs, you see, okay, this looks like that perfect relationship of an inverse function and its original function because it's that nice symmetry across the line y equals x. So that's how you do it. Boom, done. So for this one, we're going to start by swapping the y with f of x, and then after this, we're going to switch the x's and the y's. So we got x equals y plus 3 squared. And then we're going to isolate the y. So I'm going to start by taking the square root of both sides. But notice, normally this would be a plus or minus situation, but notice we've already got this nice domain restriction, which means for the function, if we originally have a nice parabola at a vertex of -3, we're only taking the right-hand side, so we're kind of ignoring that side. So it's the same thing here. We can ignore the negative side of the radical. So this means we have y plus 3 equals rad x. Last but not least, let's subtract 3 from both sides. I'm just swapping the y to this side, but it's the same thing. We got radical x on the other side, and then we're minusing 3. Now in our nice function notation, we can just rewrite this as f inverse of x equals rad x minus 3. Now let's plot these functions. So now as we graph the two functions with that included domain restriction where x is everything greater than or equal to -3, you see these two functions, like there's the original, here's the inverse, and look at that beautiful symmetry across the line y equals x pictured in green. So that's the graph, boom, done. So for this one, we're going to start by swapping out the f of x with y, and then after that, we're going to replace the x's with y's and vice versa. And then what we're going to do is we're going to isolate. We're going to subtract 3 from both sides, and then to get rid of that cube, we're going to take the cubic root, like so. And then we get y equals the cubic root of x minus 3. And of course, this is the inverse function, so let's get that nice notation. F inverse of x equals the cubic root of x minus 3. Now let's graph these out. So there we have the two functions, the original x cubed plus 3 here, the cubic root of x minus 3 here. And look at that. Again, you can see that beautiful symmetry across the line y equals x, confirming that they are indeed inverses. Boom, done. So for this one, we're starting with that domain restriction, which is only values to the right of the vertex, which again, when we're taking the radical as we find the inverse, we only have to take the positive side of the radical, not the negative side. So let's first start by replacing f of x with y. Then we're going to swap the x's and the y's. So x equals y squared plus 4y. And then to isolate y, we have to do something called completing the square. That's how we're going to isolate the y. So I'm going to take half of this b value, which is 2, square it, and add that to both sides. That's 4 on both sides. Then we got a nice perfect square on the right-hand side, which can be factored to y plus 2 times y plus 2, aka y plus 2 squared. Then I'm going to take the square root of both sides. And then I've got y plus 2 equals the square root of 4 plus x, or I can write it as x plus 4. Either way, they're both the same. I'm just going to do that because I like the way it looks. It's a little bit more consistent with the typical way these linear equations are written, x plus 4, right? And why not plus or minus? Because we're again utilizing this as a restriction to put in place here, which means basically we don't have to worry about the negative side, just the positive side. Last but not least, let's subtract 2 from both sides, x plus 4 minus 2 outside of the radical. And then in our nice function format, f inverse of x equals the square root of x plus 4 minus 2. And now let's graph it. And once we take a look at the functions here, x squared plus 4x with that domain restriction, and then the inverse square root of x plus 4 minus 2, look at that. You can tell it's perfect. It's that beautiful symmetry across line y equals x, so we know it's correct. Boom, done. For this one, we're going to start by replacing f of x with y, and then we're going to swap the x's and the y's, and now I get x equals 2 over y. Now we're going to isolate the y, multiply both sides by y, xy equals 2, divide by x, y equals 2 over x. Now that's kind of interesting because it's the exact same thing as the original function, which means this function is indeed its own inverse. So the inverse and the function are equivalent. So what does that mean? That means that this function in and of itself must be symmetric across the y equals x, because to get the inverse, it's going to be the same function. So it must have that perfect symmetry. So let's check it out. When we look at the function 2 over x, it does indeed appear to have that beautiful symmetry. Like the line y equals x is cutting it perfectly down the middle, perfectly down that line of symmetry. So that's when you're going to see that a function is its own inverse. Boom, done. So here we're going to graph the function in Desmos to figure out what the domain is. So now that we look at this function when it's graphed, we see that it's starting at -1 and kind of going up to 0, but it looks like there's a vertical asymptote at 0, and that makes sense with the denominator being x, right? So it's never going to actually touch 0. And then it seems to pick up again at 1 and go off forever and ever to infinity. So that means our domain is everything including -1 up to 0, but not including 0, union, and then starting at 1, so we're including 1, hence the square bracket, all the way to infinity. There's the domain. Boom, done. So for this one, we're going to graph it in Desmos and then find the domain from looking at the graph. So here we got the graph, and it looks like we're going from -3 up to 0, inclusive of both, right? It's including both the ending of -3 and at 0. And then we've got something picking up again, and it looks like it's at 4, which makes sense because according to this denominator, it should have a vertical asymptote at x equals 4. So then I believe it goes from 4 to infinity. So let's write that out in interval notation. So we've got from -3 up to and including 0 union, not including but starting at 4, hence the curved parenthesis, because it's an asymptote, it doesn't actually exist there, going to positive infinity, boom, done. So let's go ahead and graph this function in Desmos and check the domain. So here we have a function that looks like it's going from -3 up to +3, but then we also have all of this from negative infinity going up to this invisible boundary, which I believe is -4 because this denominator would indicate a vertical asymptote at x equals -4. So let's put that into interval notation. So as we mentioned, we're starting at negative infinity. Infinity is always going to have a curved parenthesis, not a square bracket, because we can't include infinity. It's just a concept. So we're going from negative infinity all the way up to, but not including -4, because again, it's a vertical asymptote. And then we're also adding on that range from -3 inclusive, hence the square bracket, up to and including +3, another square bracket. So there's the domain, done. So what we're going to do here is we're going to graph this using Desmos, and then we're going to look at these 3 points when y equals 0, 1, and 2. And that's going to be for the inverse function, right? And so we're going to have to find the corresponding x value. So first, let's graph this out. But so now it says that we want to know what the coordinates are for the inverse when y is 0, 1, or 2. Well, that's the same as for the regular function when x is 0, 1, or 2. So what I can do is I can find these 3 coordinates, 0, -2, 1, 0, and 2, 8. And the beauty of a function and its inverse is if these coordinates exist on the function, then the flipped coordinates, meaning -2, 0, 0, 1, and 8, 2 exist on the inverse. So that means we've got -2, 0, 0, 1, and 8, 2. So these are the 3 coordinates on the inverse with the following y values that are listed here. Boom, done. So for this one, we're going to start by graphing this in Desmos, and then we want to know the coordinates for the inverse where y equals -1, 0, and 1. So we're going to start by finding the coordinates on the original function when x equals -1, 0, 1. I'm going to show you why in a second. So now we got a nice graph of the function. I'm going to add in x equals -1, 0, and 1 so we can get our nice 3 coordinates, -1, -13, 0, -4, and 1, 5. And so you see, now I have the x values as the values that we wanted in y. But the beauty is, if I want the function inverse coordinates, it's these coordinates, but just flip-flopped. So instead of -1, -13, it's -13, -1. Instead of 0, -4, it's -4, 0. And last but not least, instead of 1, 5, it's 5, 1. So you see, we've got those y values that we wanted up here for the inverse, and these are the 3 coordinates. Boom, done. So for this one, we're going to start by replacing the f of x with y. Then we're going to swap the x and the y. So we got x equals a y cubed plus b. Then we're going to isolate y. So we're going to start by subtracting b. Then we're going to divide both sides by a. And then we got y cubed equals x minus b over a. Last step is I'm going to do the opposite of cubing, which is taking the cube root of both sides. And then that's going to cancel this out. And we're left with y equals the cubic root of x minus b over a, or in function notation, f inverse of x equals the cubic root of x minus b over a. Boom, done. For this one, we're going to start by replacing the f of x with y, and then we're going to swap the x's and the y's. So I got x equals square root of ay squared minus b. Then we're going to square both sides, and we got x squared equals ay squared minus b. We're going to add b to both sides, ay squared. Then we're going to divide a. Again, just following my typical protocol for isolating y. Now I have y squared equals x squared plus b over a. Last but not least, I'm going to square root both sides. We're going to write it up here, and I'm going to say it's equal to y equals the square root of x squared plus b over a. Last but not least, to put this into function notation, and f inverse of x equals square root of x squared plus b over a. Boom, done. For this one, we're going to start by replacing f of x with y. Then I'm going to swap the x's and the y's. Then we're going to start by multiplying both sides by that denominator. So I got x times y plus c equals, and then when we multiply the right side by the denominator, it just disappears, and we got ay plus b. Then we're going to distribute, xy plus xc equals ay plus b. Then I'm going to subtract ay from both sides, and I'm going to also subtract xc from both sides because we're going to simultaneously get these y's nice and isolated. Then I'm going to, up here, I'm going to factor out the y, and then I got x minus a on the left side equals b minus xc. Last but not least, we're going to divide both sides by x minus a. And I got b minus xc over x minus a. Going back to that nice function notation, we're just going to replace y with f inverse of x equals b minus xc over x minus a. Boom, done. And by the way, this is the same as what they have in the answer. They just flipped this by factoring out a -1 and distributed it up here, but it's still equivalent, so this is acceptable as well. So for this one, we're talking about an object that is being dropped from a height of 600 feet, being represented by this function. And now it says to express t as a function of h, aka isolate t. And then we're trying to solve for t when h equals 400. So basically what I'm going to do is I'm just going to solve, I'm going to get that t by itself. And I'm just going to represent the h of t as just h. So I got h equals 600 minus 16t squared. Then I'm going to subtract 600 from both sides equals negative 16t squared. Then I'm going to divide by negative 16, right? Just typical isolation. That cancels out. And then now I'm going to put the t squared on the right-hand side, but that doesn't change anything. It's just I like having that isolated variable on the left side. And then I got h minus 600 over negative 16. Last but not least, we're going to square root both sides. And I'm only looking at the positive radical because I'll tell you what, it doesn't make sense to look at the negative root anyways when we're talking about time. So we got this nice h minus 600 over negative 16 under the radical. And again, in the answer, what they've done is they've taken the negative down here and they distributed it up top. So you can also write this as 600 minus h over 16, but these are both equivalent. Now the last step is we're going to take that height of 400 and plug and chug. So we got 600 minus 400 all over positive 16. So that becomes square root of 200 over 16, which we'll use a calculator to approximate. And that gives us an answer of 3.535, which will round 3.54. And this is in seconds. So there's your answer. Boom, done. The surface area of a sphere is given by this equation where r is the radius. And now we want to express r as a function of a, basically meaning we isolate r. So let's say a equals 4 pi r squared. So first I'm going to divide by 4 pi. A over 4 pi equals r squared. Last step, we're going to take the square root of both sides. And now I have r equals the square root of a over 4 pi. And then it wants us to find the radius when you have a surface area of 1,000. So we're going to plug 1,000 in for a. We've got r equals the square root of 1,000 over 4 pi. Let's plug it into our calculator to get a nice approximation. And it becomes roughly 8.92. So the answer is approximately 8.92 and the unit is inches. Boom, done. So for this one, once again, we're isolating L as a function of t. So we just want to get that L by itself. So I'm going to start by saying this is t equals 2 pi times the square root of L over 32.2. Nice cursive L so it doesn't look like a 1. So we're going to start isolating. I'm going to start by dividing by 2 pi equals radical L over 32.2. To get rid of that radical, we're going to square both sides. And then we have t squared over 4 pi squared equals L over 32.2. Last but not least, we're going to multiply both sides by 32.2. And we've got L equals 32.2 times t squared over 4 pi squared. And then it's saying t represents the period, and we got a period of 2, so we're going to plug and chug and see what we get. So as we plug all this in, you see it evaluates to 3.26, rounded to the nearest hundredth. So L equals 3.26 feet. Boom, done. So for this one, we're given this surface area of a cylinder formula, and we're meant to isolate radius. Okay, so let's go ahead and do that. So first I'm going to divide everything by 2 pi. So I got a over 2 pi equals, and we're just left with r squared, and then we're getting rid of that 2 pi as well, plus rh. And by the way, it says the height is 4, so I can replace h with 4. And now we're in that situation where we need to complete the square in order to isolate r. So I'm going to add half of 4 squared, which is actually 4, to both sides. And then now I've got a nice perfect square on the right-hand side, perfect square trinomial, and I can factor it into r plus 2 times r plus 2, aka r plus 2 squared, equals 4 plus a over 2 pi. Next, I'm going to take the square root of both sides, and I'm going to put the r plus 2 on this side now because the square root cancels out the square. R plus 2 equals radical 4 plus a over 2 pi. Last but not least, we're going to subtract 2. R equals the square root of 4 plus a over 2 pi, and then minus 2. That's outside the radical. And then we're saying we need to solve for r when area is 200. So we plug 200 in here. So it's radical 4 plus 200 over 2 pi minus 2. And what we get is 3.985 rounded up to the nearest hundredth is 3.99. So the radius is approximately 3.99. The units in feet. There's the answer. Boom. Done. Consider a cone with a height of 30 feet. Express the radius in terms of the volume and find the radius of a cone with a volume of 1,000. So they didn't give us the formula, but the formula for the volume of a cone is 1/3 pi r squared times h. So it's like a cylinder with that additional 1/3. And now all we're doing is we're isolating for r, and also we're plugging in 30 for height. So if I do plug in 30 for height, I can already simplify 1/3 times 30, which is 10. So now I got volume equals 10 pi r squared, much easier, and now we can isolate. So first I'm going to divide by 10 pi, that equals r squared. Then we're going to take the square root of both sides, and I get r equals the square root of v over 10 pi. And what we're plugging in for volume is 1,000. So it ends up being the square root of 1,000 over 10 pi. Let's plug it into the calculator. And we get an approximation of 5.641, rounding up to 5.64. So r is approximately 5.64, and the units are in feet. So it's feet. There's your answer. Boom. Done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.